All right, so we have a fabulous question here. A fabulous question here. And it is the question. It's a question that everybody needs to answer in order to figure this out. And that is, which one loses voltage first? Which way does the current go? And I'm going to give you the worst possible answer, then I'm going to explain it. Ready for the worst possible answer? Worst possible answer is this. It doesn't matter. What? Think about it. Earlier when I was discussing this, I said, look, imagine there are a bunch of, let's see if I can get a marker so I can see it. Here we go, there we go, here we go. All right, so imagine for a moment that the electrons are already in the wire, right? They're there, it's metal, right? You learned last year in chemistry, there's already wires already in there, right? There is already lots of electrons in the wire. So the moment you attach this battery, every electron, every single one of them starts pushing the guy in front of them. Okay? So those electrons are pushing the guy in front of them, pushing, pushing, pushing. Now, in order for this guy to move this space here, it has to push electrons here, 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 here. So every single thing loses its voltage simultaneously. In fact, the way we look at it makes our life better is we just assume that, okay, if I'm an electron, I'm traveling through the wire, I got to lose some here, some here, some here, some here, or one of these four choices, right? I got to lose some voltage along each one of these places where I have a choice. And it doesn't matter to go backwards and forwards. You want proof? The electrons come out of the negative side of the battery. That's what we know. But remember, Ben Franklin was wrong. What he thought was moving was positive charges. So when we invented circuit theory, all of the circuit theory we've ever invented, we thought for the first 100 years, stuff was coming out of not that end of the battery. We thought things were coming out of this end of the battery. We thought things were coming this way. And because of that, we made all of our laws as if current is flowing this way. And so the answer to the question is, which way is the current flowing? It's flowing this way. Which way are things really moving? They're moving the other way. And we didn't know that, so it doesn't matter which one hits first. It can't matter. We didn't know. Okay? What you need to know is this. If you use up all your voltage here, you can't get through the remaining resistors, so nothing would happen. So you have to, every path you choose has to lose all the 100 volts. An electron that goes through this resistor here, this resistor here, and this resistor here has to lose, and this one here has to lose 100 volts along the way. Another one that goes this way, goes through this one here, goes through this one here, goes this way here, and then back down. That also had to lose 100 volts. And they have to do the same amount of volts going from here to here because it's the same drop-off. Whether they came through this system, this resistor, or this resistor over here. It has to have lost it, whether it went that way or that way. Okay? So because of that, we're looking at a problem where we have to figure out what it is, the total resistance. So what I tell you to do, and what I told you to do consistently, hopefully, is this. Find the total resistance. What does this act like one big resistor? Let's at least get one number. The one number is how much current is coming out of my battery. How do I figure that out? I have to figure out how much resistance I have in the whole entire system, because each electron, when it leaves the battery, knows everything that's in front of it. It's pushing the electrons in front of it already, right? So therefore, I'm going to look at this route here. I'm going to pretend like I'm coming out here. I'm going to actually pretend like I'm a positive battery. I'm going to be a good person. I can go this way, this way, this way, or this way. These are all in parallel, right? Well, what about the wire splitting here? Does it matter? This wire doesn't matter, so this is in parallel with this, or I can go through this one, or I can go through this one. Those are my four choices. They're all equivalent in terms of being parallel. Then, if I come out the back side, I have to go through this one here. So this one's in series, right? Keeping on going around. Then I get to here, and what happens over here? I can go this way or this way. Now, some of you might be noticing the meters, like Mr. Resdy, hey, those meters, don't worry about the meters. The meters are set up correctly. They're there to measure things, right? So hopefully they're not changing your answer. That's bad, right? Therefore, we would not hopefully have that. And then on the back side, I have a resistor here. Why? Every electron goes through here, I have to go through that one in series, right? So these are in parallel with each other. This is in parallel with each other, and this is in series. This clump, this red clump, is in series with this clump, with this guy right here, which is in clump with this clump, which is in series with this one right here. So finding my total resistance, I'm going to start with the red section. And in the red section, I'm going to go 1 over RT equals 1 over 4 plus 1 over 6. Oh, that's a 6 I drew over the top of it. 1 over 24 plus 1 over 24. Now, your math teacher would then want you to find a common denominator and do all those good things. Actually, I just did it in my head, so I'm going to pretend like I didn't. Okay, so yes, you get 1 over RT equals 1 over 2, so RT equals 2. You really should do it in your calculator because this is a physics class, and I just did the common denominator in my head while I was talking about it. All right, my bad. We'll fix this. We'll do it for real legit. Okay, so then 1 over RT over here is going to be 1 over 6 plus 1 over 2. So then that would be, I'm going to put in my calculator like a good sailor, 1 divided by 6 plus 1 divided by 2. 1 divided by shift answer, and I get 1.5. So resistance total over here is 1.5. So again, my total goal is my total resistance of the whole entire thing. And so down here I'm going to write resistance total is equal to, I go through that series, the series counts as 2, plus I go through this one over in the corner, that's 10.5. Then I go through the next one, which is 1.5, then I go through an 11. So that gives me, doing math in my head, 12, that doesn't look like a number I expected to see. 11, 12, 14, yeah, 25 ohms. Okay, that's the number I expected to see. So voltage total equals current total, resistance total. So my voltage total is 100. My current total I don't know, but resistance total is 25. So I can tell you this whole thing acts like one big 25 ohm resistor. So therefore my current would be 4 amps. Coming out of my battery, really this way, but we pretend like that way. All right. Now, I don't know how to deal with this. I can sort of deal with it. You ready to sort of deal with it? Let's sort of deal with it. We know this acts like 2 ohms, okay? Which means I'm going to drop 2 volts going from, say, here to here. Does that make sense? 2 volts. Since I'm going to lose 2 volts going across there, and it's 2 ohm resistor. Wait, why do I think 2 volts? Hold on. Had a bad moment there. It counts as 2 ohms. I don't know what I'm doing. Okay, so I know I have 4 amps going through this system, right? One way or another, it's going through the system. I have 4 amps going through the system. I've got a 2 ohm resistor. So how many volts am I going to lose going across here? 8 volts all the way across there. Okay? Then I check backside over here. I've got 4 amps coming through here. All that has to go through the 10.5 ohm resistor. So I go V equals IR for 10.5. And I get 42 volts, right? So that's 42 volts there. So I've already used up 50 volts coming on the back side. How many I got coming through here? Coming through here, I know this acts like a 1.5 ohm resistor. I got 4 amps going through it. So, sorry, yeah, 4 amps going through it. So my voltage would be equal to IR. So therefore, I've got 4 amps. Going through a 1.5 resistor, I've got 6 volts going through there. So this is 6 volts. Okay. And then I check the back side over here, and I got to figure out what my voltage is across here. I know I got all 4 amps going through that. No other choice. It's a 11 ohm resistor, so V equals IR. V equals, the current is 4, my resistance is 11, so I get 44 volts. Now, that means an electron or a charged particle traveling on the positive in the battery, which doesn't really exist, comes zipping down this wire. It loses 8 volts, no matter which way it goes through here. It loses 42 volts, so I've lost 50 volts. Then it comes to the back side. It then loses 6 volts going through here and 44 volts going through here. It's lost all 100 volts. QED, I now have all the voltages correctly. Now, that doesn't answer all the questions. I haven't answered any of the questions over the right-hand side. So now what do I do to answer the questions? Now I'm going to start going through and answering all the questions. To do that, I'm going to have to find the currents through each one of these wires. How do I do that? Aha! Here's how I'm going to do it. I choose a different color. Oh, I'm going to go this way. Okay, so I know I've got 8 volts here, correct? I lose 8 volts no matter which way I go through the system, right? So I'm going to start down here. where it's the easiest to see. Okay, I've got 8 V equals IR. I'm losing 8 volts. My current I don't know, but my resistance is 4. My current is therefore 1 amp through that choice. Okay, now I'm going to try the 6. Let's see if I can find there it is. This one right here, the 6. And so I'm going to go down here, right? V equals IR. Voltage is equal to, I'm going to lose 8 volts going through there. My current I don't know. 6 resistance, so I equals, did I do that right? No. No. Let's look up here. 8 divided by 4 is 2. There we go. That's been bothering me for a moment. Okay, so 1.33 amps going this way, correct? So that's amps going this way. And then I check, now these are parallel, these are same sort of situations, so I'm going to go V equals IR, V equals IR. I get my voltage is equal to, 8 is equal to I times 24, I equals 0.33 amps. And I'm going to do the math one more time, and I get exact same answer for the next one, right, because it's the exact same situation. Now, what do these 4 numbers have to add up to? I know I got 4 amps coming in. See if I can find my pen. Can't find my pen. Here's my pen. Okay, I know I got 4 amps coming in. I know I got 4 amps coming out the backside. So how much do I have? I have to have 4 amps. This has to add up to 4 amps. So I got 2 plus 1.33. That's 3.33, 3.66, 3.99, which is close to 4, and that's my answer. Okay, so far so good. I'm doing great. So now, what do I know? I know, as we go through the backside, let's see if I can figure this out quickly. I've got A4. Ooh, let's start with a tricky one. A4, I've got current going through here and current going through here. These two both are 0.33, so I have a total of 0.66 going through A4. 0.66 amps going through A4. Going through A5, well, I just figured that out. That's 1.33. 1.33 amps. And then I look over here, and the bottom one was 2 amps, and that's 6. So that's 2 amps. All right. A1. Well, there's all that's going through there, so we already found out a long time ago. That was 4 amps. Let's see if I can find my pen. Come on, really? Oh, that's not good. 4 amps. All right. Keeping going. The backside, everything has to go through this one here, right? So that's also going to be 4 amps. Haven't figured out these two yet, but I know I have a 6-volt drop across there, right? So I'm going to go V equals IR. Voltage equals, we said 6 volts, equals I times 6. So I'd have 1 amp going through the top route, which is A2. I'm going to do V equals IR for the other one. V equals IR. I know I'm losing 6 volts going across this thing here. So that's going to be 6 equals I times 2. I equals 3 amps. So that's going to be 3 amps. All right. If I get the volts done in the next minute and a half, we're good to go. Okay, V4 is right here. That's to measure the voltage drop going from this point here to this point here, which is across that resistor. We already found that was 42, so V4 is 42 volts. V3 is the voltage drop across here. I have to lose all 6 volts going across this one right here, so that's going to be 6 volts. 6 volts. V5, where's V5? V5, V5. V5's down here. Electron chooses, instead of going through this one to go through this one, has to lose the same amount as it loses going through that one, which is 8 volts. So I'm going to go 8 volts here. I did that wrong. That's the wrong spot. 8 volts here. V6, 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 V6 is right here. Again, lose 8 volts going this way, so therefore it does 8 volts going that way, so that's 8 volts as well. And then last but not least, with 40 seconds to spare, how much did we lose, the electron have to lose going through here? And the answer is nothing. There's no resistor here, right? So theoretically, in our perfect wire, there's no resistance at all. This voltmeter is going to read nothing. There's no change between this leg and this leg in terms of how much energy we've used up. So at the end of the day, that's going to read 0 volts. And I am done. Ask me clarifying questions. That'd be great. That's where I'll leave this video.